12, 2008, an earthquake of magnitude 8.0 struck Wenchuan, China. The catastrophic earthquake caused casualties of more than 450,000 civilians and wrecked local terrains, leading to widespread mountain collapsing and land cracking. Consequently, 90% median-span reinforced concrete bridges were damaged, such as falling beams and breaking piers, which caused road interruptions hampered following rescue activities. Investigations demonstrate that pre-stressed, reinforced concrete simply supported beam bridge has disadvantages of heavy weight, poor structural integrity and ductility, which cannot fully meet requirements of bridges in high-intensity seismic regions. How to improve seismic resistance performance of median-span bridges in an economical and environmentally favorable manner has become a key engineering problem. Over the past years, massive experimental researches demonstrate that concrete-filled steel tube, CFST, has the advantages of high strength, good ductility, and light structure weight. Application of CFST on bridge can reduce its weight and improves its seismic resistance capability. Keku Bridge locates in 5.12 Wenchuan seismic active fault zone, which has a peak ground acceleration of 0.35 grams, with a probability above 2% in 50 years. Engineers created a new full CFST truss structure for the 6,431 meters long Wenchuan Keku Bridge, which adopts 40 meter span CFST truss girders and CFST piers. Challenges from seismic resistance requirements are satisfied in three issues: reducing structure weight, improving pier resistance, and developing a seismic structural system. Lightening structure, reducing seismic response. The girder employs two CFST longitudinal trusses anchored to steel concrete composite bridge deck through two longitudinal ribs. The girder is 4.2 meters high, deck ribs is 70 centimeters high, and deck plate is 15 centimeters thick. The space between two CFST longitudinal trusses is 7 meters, each of which is composed of a pre-stressed CFST main tube and CFST branch tubes. The empty main tube is used as the support for pre-stressed tension, then concrete is poured. After concrete reaches its design strength, pre-tension is released. Then pre-stressed CFST main tube is formed. The ultimate bearing capacity of CFST can be increased by 1.5 times. The steel concrete composite bridge deck is composed of 6 mm to 8 mm thick bottom plate and 6 mm thick perforated reinforced shear steel plate and C40 steel fiber concrete. Its ultimate bearing capacity is 1.6 times to RC deck. Integrity of girders is ensured with longitudinally lying transverse steel tube trusses at an approximate 14 meters interval in between to form a strong transverse connective structure. It has been verified by experiments that through scientifically matched structural parameters of main tube and branch tube with filled concrete, full penetration welding and weld surface grinding, the nominal stress amplitude of intersecting welded joint is lower than limited stress and meets the requirements for infinite fatigue life. Top tie tube is used to connect the standard piers with CFST columns of 1.3 meters in diameter. Instead, pre-stressed steel box concrete cap beams are used to connect the non-standard piers which cross over obstacles. The ultimate bearing capacity is 1.5 times of RC cap beams. Compared with RC girder bridge, The girder and pier's weight of truss bridge is reduced by 35% and 60% respectively, and seismic response of its pier column is reduced by 37%. Compared with the steel girder bridge, the main girder of CFST truss bridge has a similar weight, but its steel consumption is reduced by 38%. Moreover, its rigidity is increased to 2.6 times, and internal force of pier column is reduced by 23%. Strengthening pier columns to improve seismic resistance. Experiments and studies show that concrete have obvious brittleness and low strength, while CFST has higher strength and better ductility due to restrained hoop effect from steel tube on filled concrete and reacting supporting effect on tube from concrete respectively. As a result, CFST pier columns have better structural seismic resistance, bearing capacity, and energy dissipation performance. The pier pile joint of RC bridge locates at potential plastic hinge area and thus is prone to damage. Therefore, CFST pier with improved joint is adopted instead to this bridge. Steel tube welded with perforated steel plate has shear holes, steel ring, and extra steel tube coat. Self-compacting concrete is poured into steel tube to form strengthened steel concrete composite joint, which ensures pier remaining in elasticity state under earthquake and achieves a safety coefficient of 8.0. This ingenious design serves like an ankle supporter, which protects the bridge's ankle from potential damage. Excellent a seismic system. Group piers bearing controllable response. The 150-meter-long girder in existing multi-span beam bridge structure system is mounted on piers through horizontal equivalent rigidity bearings. Such seismic rigidity is low, and bridge piers have large internal seismic response, which is prone to falling and collapsing during earthquake. The seismic pier group structure system developed by our engineers has well-balanced force distribution, increased union length more than 300 meters, increased whole bridge rigidity, and enlarged number of engaging bearing piers during earthquake. Meanwhile, the developed seismic bearings with the same dimension and designable horizontal rigidity is applied. The horizontal rigidity of bearing is matched with pier, so that the internal seismic response of each pier is close. The seismic structure system correspondingly reduced peak internal force of pier by 53% and girder displacement by 85% during earthquake. The seismic resistance of Wenchuan Keku Bridge has been improved from multi-dimensions: CFST truss structure with reduced weight, CFST material with high strength and good ductility, strengthened pier pile joint, and seismic structure system of pier group with balanced force. Since the 21st century, global seismic fault zones have entered into a new active period. In the past 10 years, several catastrophic earthquakes occurred in China, such as Wenchuan 5.12 disaster. The high seismic activity regions accounted for 41% of the total area in China. According to the development plan, a large number of medium-span bridges in highly seismic areas will be built. Seismic resistance technology developed from Wenchuan Keku Bridge will provide the best choice for medium-span bridges at high-intensity earthquake regions in China and around the world.